let's discuss the current quantum mechanical model of the atom. Erwin Schrödinger gets the credit for the current quantum mechanical model. Schrödinger's description of the atom is a major change from atomic models of the past. In the past, atomic models focused on physical descriptions of the atoms. Protons are positive, protons had to be in the nucleus, negative electrons were orbiting outside the nucleus, protons are more massive than electrons, statements of physical properties like that. Schrödinger's atomic model is based on solutions to calculus equations and quantum physics concepts. The quantum mechanical model originates from de Broglie's proposition that an electron could be thought of as a standing wave. Wave equations to describe standing waves were already well established. Schrödinger took these known equations and used them to describe the wave-like properties of the electron in a hydrogen atom. This resulted in a wave function, represented by the Greek letter psi. The upper-level calculus of the quantum mechanical model is way beyond our capabilities in high school AP chemistry. So we can't actually use these wave functions and calculate our own answers. What we can do is use the knowledge gained from other people solving the wave functions. Solutions to these wave functions describe the structure of the electron cloud of an atom. It tells about the arrangement of the electrons around the nucleus. And that's very important for a chemist. How an atom acts chemically is based on the arrangement of its electrons. When studying waves, remember that this was well-established science at the time. There's a relationship between the intensity of light and the square of the amplitude of the wave. Max Born applied this idea to the electron wave to show that the square of a wave function tells you where an electron is likely to be. In other words, the solution gives you the probability of finding an electron in a particular region of space in the atom. That vocabulary should sound familiar to you. It should remind you of your discussion of orbitals in Chem 1. Solving the wave functions for the hydrogen atom gives you several integral numbers called quantum numbers. You probably heard about these, at least briefly, in Chem 1. I will be discussing them in the next video. A solution to a wave function gives you 3 quantum numbers. This solution defines an atomic orbital. An orbital is a mathematical expression. It represents a 3D region of space where there's a high probability of finding an electron. The previous atomic model, the Bohr model, proposed that electrons exist in certain allowed orbits around the nucleus. The quantum mechanical model, on the other hand, does not define the exact path of the electrons. Instead, the model describes, via calculus, regions around the nucleus where electrons will be found, which we call orbitals. While he did incorporate the idea of quantized energies, the Bohr model was still based primarily on classical physics. Schrödinger's quantum mechanical model is based fully on calculus and quantum mechanics. So scientists have been solving these wave functions for a little under 100 years now. The solutions describe an array of regions around a nucleus where we're likely to find electrons. These regions are called orbitals, and they come in several different shapes. S-type orbitals are spherical. P-type orbitals are usually referred to as dumbbell-shaped. I think of them like 2 inflated balloons held together at the tied-off ends. In a given energy level, there are 3 p-type orbitals. The only difference between them is their orientation in 3D space. Like here, one orbital is shown on the x-axis, one on the y-axis, and one on the z-axis. D-type orbitals are more complex. 4 of the 5 look like four-leaf clovers, again differing in their orientation in 3D space. The 5th D-type orbital looks like a p orbital with a ring around the middle. F-type orbitals are even more complex, as you see here. In the quantum mechanical model, Bohr's energy levels are now called principal energy levels. They are definitely not paths for the electrons to travel. Principal energy levels are divided up into sublevels, labeled as S, P, D, and F. The number of sublevels present in any given energy level is equal to the energy level number. For example, energy level 2 has 2 sublevels. That would be S and P. Energy level 3 would have 3 sublevels, S, P, and D. Sublevels are further divided up into individual orbitals. The S sublevel has only 1 orbital. The P sublevel is 3 orbitals. We saw those earlier. Remember, they differ only in their 3D orientation. The D sublevel has 5 orbitals, and the F sublevel has 7. Knowing this structure for atoms, we can write what is called an electron configuration for a given atom. This tells the location of every electron in the atom. The notation that we use is a repeating pattern of the principal energy level number, the letter of the sublevel, and an exponent representing the number of electrons in the sublevel. There are several rules governing the location of electrons in an atom. Here are 2 that we need to know now. First, only 2 electrons can exist in a single orbital. Second, electrons always exist in the lowest energy orbitals possible. This means we need to know the order of orbitals in terms of their energy. There are 2 ways to know the order of orbital filling. You can draw and use a diagonal diagram, or you can use the periodic table. To draw a diagonal diagram, start at the bottom with 1s and write the sublevels in columns and the principal energy levels in rows. Then, draw diagonal arrows from bottom right to top left. Now you read 1 arrow at a time to know the orbital order. The first arrow at the bottom shows 1s. The next arrow shows 2s. The next arrow shows 2p, followed by 3s, and so on. This method is functional, but a little cumbersome to use. What's faster is using the periodic table to tell you the order of the orbitals. The periodic table is broken into blocks associated with the sublevels of the outermost electrons of those atoms. For example, any element in the first 2 columns has their outermost electrons in an s sublevel. These 2 columns are called the s block of the periodic table. Every element in column 1 of the periodic table has 1 electron in an s sublevel. For all these elements, their electron configurations end with the highest principal energy level number followed by S1 every time. For column 2, their electron configurations end with some number followed by S2. Notice that helium is not drawn in this block of the periodic table, but it is still considered an S block element. The first principal energy level is so small that it can only hold 2 electrons. Helium, with 2 electrons, has that level filled, which is why it definitely belongs in the last column with the noble gases and their full outer shells. Helium is an s block element because its last electron is in the 1s sublevel. The 6 columns on the right-hand side of the periodic table constitute the p block of the periodic table. All these elements have their last electrons in a p sublevel. Likewise, the middle transition metal section is the d block, and the inner transition metals are called the f block. The principal energy level for any set of orbitals is related to the row number. For s and p block orbitals, the principal energy level is the row number. For d block orbitals, the principal energy level is 1 less than the row number. And for f block orbitals, the principal energy level is 2 less than the row number. Let's look at a few examples. Write the electron configuration for the element sulfur. Let's do this off the periodic table. Start at the top left of the periodic table, go left to right, top to bottom, and write each level and number of electrons until you get to the element sulfur. This means going through 1s2, 2s2, 2p6, and 3s2. How far into the next level do we go to reach sulfur? We go 1, 2, 3, 4 squares in. So the electron configuration ends with 3p4. That gives us 1s2, 2s2, 2p6, 3s2, 3p4. Let's try bromine. Starting at the top, we again go all the way through 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. We then reach the d block. Remember that the principal energy level of these electrons is 1 less than the row number, so we'll write 3d10. Then we have to go 5 squares into the 4p section to get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. You probably recall from your Chem 1 class that there's a shortcut we can use here. We can actually start at the noble gas that precedes bromine on the periodic table, in this case argon. Noble gases have a full outermost energy level. This means their arrangement of electrons is very stable. Noble gases never spontaneously chemically react. So instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, we can write AR in brackets. We then write the rest of the electron configuration in the same way. Take a look at the element yttrium. Starting at the previous noble gas, we would then go through 5s2 and 1 block into the 4d section, giving us Kr in brackets, 5s2, 4d1. We're going to do one more example, the element platinum in row 6. There's something you need to remember about rows 6 and 7. Notice here that the atomic numbers jump up. This is where the inner transition metals fit into the main body of the periodic table. The inner transition metals actually fit into the periodic table after the elements lanthanum in row 6 and actinium in row 7. Lanthanum is filled at 6s2, 5d1. Likewise, actinium ends with 7s2, 6d1. Electron configurations of the inner transition metals vary greatly. They're not predictable in this method that we're using for the rest of the elements. So you won't be asked, to write their electron configurations this way. When you look at elements beyond the inner transition metals, what the periodic table actually shows is one electron going into the D sublevel, then the F sublevel filling completely, then further electrons being added to the D sublevel. We're going to simplify this just a little bit. When you're asked about elements beyond the inner transition metals, you know that the F sublevel is completely filled. So after the S sublevel, 6S or 7S, write the full F sublevel. Then start on the D sublevel after that. So for the element platinum, I would start at xenon, then write 6s2. Then I would include the full F sublevel. Remember that for the F block, the principal energy level is the row number -2. The top row of the intertransition metals is from row 6 of the main table, so we'll write 4F14. Then we go back and start at lanthanum in the D block. That would give us 5D8. The electron configuration then is xenon, 6s2, 4f14, 5d8. There are a few regular exceptions that you need to know about in the D block. Regular exceptions is probably a misnomer. These are not exceptions to real life. These are describing how reality really is. I guess I should call this one additional rule to writing electron configurations on the periodic table. This additional rule is based on the fact that atoms are more stable when they have full or half-full sublevels. Of course, a full sublevel represents stability. It's full. You need no more or no less. A half-full sublevel also imparts stability. If a sublevel is half full, every orbital in that sublevel has one electron in it. As an example here, look at the element chromium. Based on what we've learned up to now, we'd write that the electron configuration is argon 4s2 3d4. But if we were to rearrange our placement of the electrons, we could make both the 4s sublevel and the 3d sublevel half full. And this is what really happens. In an atom of chromium, one electron bumps up from the 4s sublevel into the 3d sublevel. The correct electron configuration, the way chromium really exists in the world, is as argon 4s1 3d5. This rewrite applies to all the elements in the fourth column of the D block. Something similar exists for writing the electron configurations for the elements in the ninth column of the D block. Look at silver, for example. Before, we would have predicted its electron configuration to be krypton 5s2 4d9. We now know that one electron actually bumps up, leaving the 5s sublevel half full and making the 4d sublevel full. The correct electron configuration for silver, then, is krypton 5s1 4d10. Exceptions also occur throughout the F block, but there's no regularity to them. You don't have to know any F block exceptions. Closely connected to electron configurations is the process of drawing orbital diagrams. Electron configurations tell you how many electrons are in an entire sublevel. Orbital diagrams break it down a step further to show you the location of the electrons in each individual orbital. In an orbital diagram, you draw a box or a line to represent each individual orbital. You draw up and down half arrows to represent the electrons. We talked about a few rules for writing electron configurations. Here we need a few more rules that apply to orbital diagrams. First, electrons enter degenerate orbitals singly before pairing. The word degenerate here means of equal energy. All the p orbitals in the 2p sublevel are degenerate, for example. They are equal energetically. The only difference between them is their orientation in 3D space. What this rule means in simpler terms is that electrons won't pair up in an orbital until they have to. Additionally, when they do pair up, electrons in the same orbital must have opposite spins. We use up and down half arrows to represent spins. Draw an orbital diagram for the highest occupied sublevel of nickel. First, what is the highest occupied sublevel? In other words, what is the last thing you would write in its electron configuration? That would be 4d8. How many orbitals are in this sublevel? Because it's a d sublevel, there are 5 orbitals. The number of orbitals has nothing to do with the principal energy level. The number of orbitals is determined by the type of sublevel. S-type sublevel, 1 orbital. P-type sublevel, 3 orbitals. D-type, 5. F-type, 7. How do electrons fill these orbitals? Hund's rule says that electrons won't pair until they have to. Even more specifically, Hund's rule says that for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. Putting all that together means put electrons into separate orbitals drawn with the same spin for as long as possible. When each orbital has 1 electron in it, then you have to show electrons paired. Remember that the previous slide said that electrons in the same orbital must have opposite spins. The second electron in each box must be drawn oppositely. What if I started pairing electrons from the right-hand side? Is that a problem? No, because all these orbitals are degenerate. They are equivalent. I could choose any 3 boxes to pair the electrons in. What if I'd use down arrows first? Is that okay? Yeah, that's okay too. You just have to write the opposite arrow when you pair them in an orbital. Draw an orbital diagram for the highest sublevel of the element tin. The highest sublevel reached is 5p with 2 electrons in the sublevel. How many boxes do you draw, and why? You should draw 3 boxes because it is a p-type sublevel. You have 2 electrons to put in the boxes. They will go in singly. A common question that relates to orbital diagrams is how many unpaired electrons in an atom of blank. Your answer is based off of the orbital diagram for the highest occupied sublevel in that atom. How many unpaired electrons do you see in that orbital diagram for nickel? You see 2 in those last 2 boxes. Here you have electrons in a box without a partner. That's an unpaired electron. How many unpaired electrons in an atom of tin? The answer is 2 again. What is this third empty box? It is an orbital that is currently unused. There are no electrons in that orbital. To finish, there are 3 rules that we've seen regarding the placement of electrons in atoms. First is called the Aufbau principle. This is the rule that tells us electrons fill lowest energy orbitals first. Please, note that Aufbau is not the name of a dead scientist. It's a German word that means to build up, to construct. Hund's rule is named for a dead scientist. It tells us that electrons won't pair up until they must. And the Pauli exclusion principle says that electrons in the same orbital must have opposite spins. We will discuss these same rules again after studying quantum numbers in the next video.